Any computation requires memory. When a machine like a computer performs computation, it needs to remember its state. Electronic circuits like latches and flip-flops can hold memory. Computers use those memory circuits. Biological systems like a cell also need memory, a memory of its molecular states. Can we design a genetic circuit that will work like a latch or flip-flop circuit? This video is all about that. We'll investigate a simple genetic circuit that works like a set reset latch with memory. I was inspired to create this video after watching the YouTube video by Sebastian on latches and memory circuit. You may also enjoy that video. I have given a link here. We will use concept of bifurcation plot, phase portrait, null line, and stability of steady states. I hope you understand these concepts. Otherwise, please go through my YouTube videos on this topic. The link is given here. Fine. Back to set reset latch, a circuit that holds memory. Here is a simple set reset latch circuit. It is made up of 3 logic gates: OR, AND, NOT. A OR gate has 2 inputs and 1 output. The truth table shows the input-output relations. When both the inputs are 0, the output is 0. For any other input combination, the output is 1. AND gate also has 2 inputs and 1 output. When both the inputs are 1, the output is 1. Otherwise, the output is 0. Now the NOT gate. It has 1 input and 1 output. It flips 1 to 0 and 0 to 1. Let's see the behavior of the set reset latch circuit. This circuit takes 2 inputs and gives 1 output. Inputs are either 0 or 1. 0 means switched off or no signal. 1 means switched on or having a signal. Outputs will also be either 0 or 1. One input is called a set signal. This is used to set the memory. The other is the reset signal. This signal erases the memory. First, switch on the set signal. The OR gate now has 2 inputs. One is 1, the other is 0. So the output from this OR gate is 1. This 1 goes to the AND gate as one of the inputs. The other signal is coming from the reset switch. This switch is off. That means it is 0. So the input to the NOT gate is 0. It will flip it to 1. So both the inputs to the AND gate is 1. That means the output from the AND gate is also 1. Note that this output feeds back by a feedback as an input to the OR gate. That means both the inputs for the OR gate are now 1. Now we switch off the set switch. So the inputs to the OR gates are 0 and 1. With these 2 inputs, the output from the OR gates stay 1. Similarly, the output of the circuit as a whole also stays 1. By now, you must have noticed the memory effect. We get the output of 1 by setting the set switch to 1. Then we switch it off. Even then, the output of the circuit stays at 1. So the circuit remembers its previous state. To erase this memory, we have to switch on the reset switch. Then the output from the NOT gate will be 0. So that will set one input for AND gate to 0. This will in turn generate an output of 0. That feedback will also become 0. So the output from the whole circuit will be 0. The memory is erased. Now I can switch off the reset switch. The circuit is set to the initial condition. I have implemented this set reset latch in a genetic circuit of 2 genes. S is the set signal. It induces the production of X. X induces the production of Y. Y in turn works as a positive regulator of the expression of X. So this is a positive feedback that we need in the latch. Y is also the output of our latch. Expression of Y is inhibited by I, an inhibitor. This is the reset signal of the latch. Note that the expression of X is controlled by two regulators, S and Y. Consider that the promoter elements are such that these two regulators are working independently. So we consider this is as an odd type regulation. One input either from S or Y is good enough to induce the expression of X. Expression of Y is regulated by I, the inhibitor, and X. Consider they had an AND type regulation and they work concurrently. The expression of Y is induced by X, but this induction is inhibited by I. Here is the ODE-based model for this genetic circuit. Let's check the first ODE. The first term on the right hand side is a Hill function representing the induction of expression of X by the set signal S. The second term is also a Hill function, but this represents induction by Y. Notice that both Y and S are inducing the expression. However, they are controlling the expression of X independently. So, it is an OR type regulation. The last term in this ODE is for degradation of X. Now the second ODE. This is for Y. On the right hand side, we have a Hill function representing the induction of Y by X that is multiplied by an inverse Hill function. This one is for inhibition by the inhibitor I. So X and I are working together to control the expression of Y. When I is 0, there is no inhibition. X will be able to induce the expression of Y without any inhibition. But as I increases, the effect of X will decrease. They are working together, so this is equivalent to an AND type regulation. The last term in this ODE is for the degradation of Y. To analyze this circuit, I have assumed some values for parameters in this model. N equal to 3, D1 equal to D2 equal to 0.5. Both S and I will be either 0 or 1. 0 means off, 1 means on. Here is the phase portrait of the system when both S and I are 0. It is the resting state. It has 3 steady states. The green steady states are stable. They are sync nodes. The red one is a saddle. The lower green steady state, which is on the stable, is at X equal to Y equal to 0. So, if we start with a low value of X and Y, the system will eventually reach this stable steady state at X, Y equal to 0. Now, switch on the set signal. That means you set S equal to 1. That will change the phase portrait. This is the phase portrait of S equal to 1 and I equal to 0. Now notice the system has only one steady state at a high value of X and Y. This steady state is stable. It is a sync node. That means whatever be the initial position of the system, eventually it will reach this steady state. You must have noticed that the number of steady states and their stabilities are changing with the value of S. When S equal to 0, I equal to 0, we had 3 steady states, out of which 2 were stable. Now as we change S equal to 1, we have only 1 stable steady state. That means the system has bifurcation, and S is a bifurcation parameter. Here is the bifurcation plot considering S as a bifurcation parameter. Here inhibition is absent, so I equal to 0. The blue lines are the stable steady states. Pink is unstable. When the set signal is very high, say S equal to 1, there is only one steady state which is stable. When S is 0, there are 2 stable steady states. One of them is 0, 0. Suppose initially there is no set and reset signal. That means S equal to 0, I equal to 0, and the system is at a steady state with Y equal to 0. So the output from this circuit is 0 because we are considering Y as the output from the circuit. Now we switch on S. So we set S equal to 1. So with time the system will reach a steady state where Y is near 2. So we have a high output from the circuit. We consider this as an on state for the system. After some time, switch off S. So S equal to 0. With time, the system will move to a steady state slightly lower than the previous one and near y equal to 1.5. Notice the interesting behavior here. Although we have switched off the set signal, the output y is still at a high non-zero value. That means y is still at the on state. This is what happens in a set reset latch. The system has a memory of its past and it stays in the on state even after I have switched off S. So what will happen if we now switch on the reset signal? To answer that, we need to change I from 0 to 1. Here is the bifurcation diagram considering I as a bifurcation parameter. Note, we are keeping S equal to 0 here. S equal to 0, I is 0 and Y is at a steady state near 1.5. If I change now I to 1, with time Y will reach a lower steady state at Y equal to 0. The output from the circuit is now 0. So the memory is erased. The latch is set to the initial condition. I have also done numerical simulation of this circuit. So here is the data from that simulation. Initially, S, I, X and Y all are 0. Now I switch on the set signal by setting S equal to 1. Y reaches a high value near 2. This is the on state of the circuit. After some time, we switch off S. Y drops slightly but stays close to 1.5. It is a high non-zero value. So we can say the circuit is still in the on state. After some time, I want to reset the circuit. So the reset signal is set on. This is achieved by making I equal to 1. That makes Y equal to 0. So the system is reset to the initial off state. We can switch the system on again after some time by setting S equal to 1. So in brief, we have got a molecular version of the simple set reset latch. Both of them, the electronic one and this genetic circuit, use OR and AND logic. The NOT gate in the reset signal is represented by the transcriptional inhibitor. Both circuits employ positive feedback. In fact, this positive feedback is responsible for the bifurcation and memory. Many cellular processes require molecular memory, and that is achieved using suitable positive feedback. That's all for this video. Happy learning.